Okay, so last time I talked to you guys, it was like 2 weeks ago. Yeah, 2 weeks ago. I was explaining radioactive decay and how elements can become more stable or have a more stable nucleus by either changing protons to neutrons and releasing a positron, or they can release an alpha particle, which is the nucleus of a helium atom, 2 neutrons, 2 protons, or a neutron can become a proton by releasing a beta particle, which is basically a negatively charged, so kind of like an electron. And what was the other one? There's gamma rays, all kinds of ways that unstable nuclei can become stable. So the what do you call it? Topic for today is discussing half-life and how we can use that to date certain objects that we find, especially like in archaeology, when they go and they find things that are like really, really old. We can use half-life to help figure out how old they are. Anyway, so the point of half-life is that no two radioactive isotopes decay at the same rate. So every unstable nucleus is going to decay at a different rate. And half-life is the time required for half of the atoms of a radioactive nuclide to decay. This is an example of a half-life graph. And this happens to be for radium-226. And you can see it takes quite a long time to decay. So here's an example of a question that might be asked about half-life. If you've got phosphorus-32, has a half-life of 14.3 days. How many milligrams of phosphorus-32 remain after 57.2 days if you start with 4 milligrams of the isotope? So I hope you don't hear my husband yelling in the background. He's downstairs playing Call of Duty, and he's quite loud when he does that. Okay, so the solution for this is to determine the number of milligrams of phosphorus-32 remaining. We must first find the number of half-lives that have passed in the time elapsed. Then the amount of phosphorus-32 is determined by reducing the original amount by half for every half-life that has passed. So we have the number of half-lives equals the time elapsed in days times 1 half-life over a 14.3 days, because that's what it tells you in the original question, that the half-life is 14.3 days. So we have the amount of phosphorus-32 that remains is equal to the original amount of phosphorus-32 times half for each of the half-life number, for the number of half-lives that you've calculated. So then we do the calculations. We've got the number of half-lives. We've got 57.2 days, which is the time that they gave us in the question. And we multiply that by the conversion factor of there's 1 half-life for every 14.3 days as per the data given in the question. So we calculate, that's covering the answer. So it's that's calculating how many half-lives have occurred over the amount of time given. So then we have the amount of phosphorus remaining is equal to the original amount, which was 4 milligrams. They gave us that up here, 4 milligrams. And we calculated that there are 4 half-lives in 57.2 days. Excuse me. So we multiply it times 4 half-lives, and we get 0.25 milligrams. Should be pretty easy, easy peasy. So when you're given a question like this, you calculate how many half-lives have passed over the amount of time that they gave you, and then you take the original amount and you multiply it times however many half-lives you calculated. Now, the next thing is decay series. So one nuclear reaction is not always enough to make a stable nuclide. So for example, if you start with, say, uranium-230, is it 235 or 238? I can't remember. The one that they used for nuclear bombs and nuclear power. It's not like for every nuclide that you just maybe release like one positron and you're stable. Sometimes it takes like multiple steps to become stable. So a decay series is the series of decays that occur until a stable nuclide is reached. Now, each particular unstable nuclide is going to have a very particular decay series. So it never changes. It always it always follows the same steps. So when we start with the original unstable nuclide, that is called the parent nuclide. Oh, there's ice. Okay. So as I was saying, decay series is like basically the steps of an unstable nuclide forming a stable nuclide. The unstable one that you start with is called the parent, and the nuclides that are produced by the decay are called daughter nuclides. It's a lot similar to what we talk about in biology, the parent cell and the daughter cells. So we use the same adjectives to describe that. All naturally occurring nuclides with atomic numbers greater than 83, which I believe is bismuth. I mentioned that feels like a month ago, even though it was only 2 weeks. That the elements that have nuclei heavier than 83 are going to be unstable. I think it's bismuth. So there's 3 natural decay series. So to correct myself from what I said before, it's not that or to make it clear, I don't know how I said it before, but just to be clear, all of the unstable nuclei are going to follow a particular decay series in order to become stable. So the 3 decay series, the parent nuclides are U238, U235, I guess that was both of them, and TH232. So here is the uranium-238 decay series. So if you have any nuclide within this series, say you have a radon-222, then it will follow this particular series, but from this point. I hope that makes sense. So you start with U-238, and can anyone tell me what kind of decay this first step is? Going from U-238 down to TH234. So just to review, we went from 238 and atomic number of 92, and we went to 234 and atomic number of 90. Can anybody identify what kind of decay that is? Oops. Why did I write 29? 90. Okay, so what you have to do is look at how much the atomic mass decreased by. So atomic mass decreased by 4, and you look at atomic number decreased by 2. And there's only one type of decay that I talked about 2 weeks ago that matches this kind of reduction in both atomic mass and atomic number, and that's alpha. So it released an alpha particle. And you can go through each one of these and identify what kind of, or you could just look at the key down there. For each of these steps, you can go through and identify what kind of decay each step is. But the point is basically that this is the decay series for U-238. And like I said, if you have an element in there that falls under any one of these steps, then it will follow this decay series for the remainder until you get to lead-206, which is the stable nuclide. So you start with the parent nuclide, which is U-238. And as it decays, it emits an alpha particle like I just showed you. And we know that because the mass number decreased by 4, the atomic number decreased by 2. Now, on the left-hand side, let me just go back for a second to make sure that I should have started this first, actually. Identify what the y and the x-axis are. So the y-axis is atomic number, and the x-axis, that's hard to say, x-axis is the atomic number, mass number, atomic number. Oof, my brain doesn't work very well on a Monday. Not after having a week off. All right, so now we identify the first step, which is alpha decay. Oh, and I went by it again. So because we have mass number on the y-axis and we started at 238, we moved down 4 units to 234, and we put our new daughter nuclide on the 234 mark. Now this is going to, on the x-axis, match the 90 position because we haven't, because we've also gone down or gone to the left by 2 units, you can see there. The atomic number, like I said, decreased by 2. So again, your horizontal position, you go down by 2. And so the new daughter nuclide is an isotope of thorium. And so here would be the alpha decay nuclear reaction for that particular first step. It also tells you here the amount of years that it stays stable. So that stays stable for 4.5 times 10 to the 9th years. That's quite a long time. So the half-life of thorium, 234, which is the first daughter nuclide, is 24.1 days. So if you think about just, oh, it's up here anyway. You've got U-238, which has a half-life of, what is that? 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom, boom. What is that? 1,000, million, billion? 4.5 billion years. That's the half-life of U-232. I can't talk today. U-238. So 4.5 billion years. That's, by the way, the age of the Earth. That's the half-life. And then the thorium-234, 24 days. So after 24 days, half of it is going to decay and is going to give off beta particles. So for beta particles, we do not decrease in atomic mass, that stays the same, but we do decrease in atomic number by 1, because we've got the beta particle, which is basically a negatively charged particle. This also increases its atomic number because we go from 90 to 91. So we have to move to the right by 1 unit because the x-axis is atomic number. But mass number, therefore the vertical position stays the same because we're still at 234. Okay, and you can follow that all the way down for the whole series. I'm not going to go through every single step because that would be super boring, and you can do that on your own if you feel like it. But in the final step, polonium-210 loses an alpha particle, so we're over here, loses an alpha particle to form lead-206, and this is stable. Okay. Now, just to draw your attention to the atomic number, it's 82, so it has 82 protons, and that is a magic number. If you remember back to the magic numbers, there's a certain number of protons and or neutrons where the nuclei is stable, and so 82, I think, is the highest. Okay, so that's all natural radioactive decay. But artificial radioactive nuclides are not found naturally on Earth. That's why we call it artificial. These are caused by the bombardment or hitting the nuclei with charged and uncharged particles in a process called artificial transmutation, literally just meaning like mutating it artificially, like we're making it happen. Because neutrons don't have a charge, if we shoot neutrons at a nucleus, they can penetrate. Positively charged alpha particles, protons, anything that has a positive charge is going to be repelled by the nucleus. And so if you wanted to transmutate a nucleus using a positively charged particle, it would take a great amount of energy. This energy can be supplied by accelerating the particles in a magnetic or an electrical field of a particle accelerator. Trying to see if there's any kind of reference point on the picture. The whole circle is the particle accelerator. That's the whole thing. All it does is just accelerate particles so then you can like smash them into atoms. I do believe this is a road back here, if I'm not mistaken. Oh, it's like a big lake here. Maybe that's a road. I don't know. But it's really, really big. I think there's like several kilometers in diameter. Radioactive isotopes of all natural elements have been made by artificial transmutation. The production of technetium and promethium by artificial transmutation fills gaps in the periodic table. So all of these guys here, and rip, those are all artificially made elements. We've created those in the lab. Well, I should say in the particle accelerator. So the elements that have more than 92 protons in the nucleus are called transuranium elements. So you can see them here from 93 to 103. And you can see the nuclear reaction that created them. So all of these elements you're looking at were all created by us. They're not naturally occurring. Currently, there are 19 named, although I'd have to double check that. I wouldn't be surprised if it's a lot more than that, because on the periodic table that I usually hand out, there's the bottom right, not in the lanthanide actinide series, not in the F block, but in the period 7 all the way on the right-hand side, you had like UUU, UUN, UUM, things like that. I think some of those have been named now. Okay,